My name is Mahmoud Ismail. I'm a specialist solution architect at AWS, and I help customers with their cloud journey. I'm delighted to share the stage with Paul.
Hi everyone, my name is Paul Rapper. I'm a senior staff software engineer at Slack.
And welcome to our session, Learn to create a robust, easier to scale architecture with cells. For today's agenda, I'll take you through what a typical customer journey looks like and some of the challenges that we see customers face. I'll then talk through some common failure scenarios, introduce cell-based architecture, along with important concepts like cell observability and deployment. And then I'll hand over to Paul, who'll talk about what they did at Slack. So what does a typical resilience journey look like for a customer? It usually starts when there's a high impact incident that happens within an organization, raising some eyebrows. Then this will lead to a driver to improve the overall resiliency and efficiency of the architecture. And then, the goal of this was to come to maybe a program of work can be created with the goal to reduce the restoration time and the detection time, along with increasing the mean time between failures. So organization experiences high impact incidents. There's a driver to improve the overall resiliency of the infrastructure and architecture. And then the goal is to lower the detection and restoration time, along with increasing the time between failures. So the issue becomes, how do we minimize the impact of these incidents? So there's three main concepts I'd like to talk about here. The first one is blast radius. It's important to reduce the impact of failures when they happen and to contain the failure to be within a boundary that you set. What we're trying to do here is reduce the percentage of customers that are impacted. Second is observability, which is the ability to detect problems early and mitigate them. What we're trying to do here is reduce the mean time to detect and the mean time to repair. These are two very common metrics in the field of resiliency. And then there's deployments. How do we reduce the impact of a bad deployment when you're pushing out code to your infrastructure? And what we're trying to do here is increase the mean time between failures. So let's talk about some common failure modes. But before that, I'd first like to talk about fault isolation boundaries. Fault isolation boundary is basically a way to contain the failure to be within a defined boundary that you set. Anything outside of this boundary is unaffected and will continue to function as normal. From an infrastructure perspective, we have AWS regions, which are physical locations around the world, all independent from one another. And you could actually say that a region is a fault isolation boundary. Zooming in, a region has multiple availability zones, and every availability zone is an isolation boundary with multiple data centers and high levels of redundancy already built into it. The focus of this talk is about AZ fault isolation boundary. The idea here is to understand the fault isolation boundaries that are available to you so you can architect your workload in such a way that you reduce the impact of failures when they happen. If you'd like to know more about this topic, you could scan the QR code here and it'll take you through our white paper. We'll go into more depth. Okay, so let's talk about the failure modes, starting with the gray failure. Let's say you have a system that's a dependency for three applications, applications 1, 2, and 3. Now, each of these applications is sending the latency metric to a core business logic of the system, which in turn sends a report to the observer, which is seeing an average latency of 53 milliseconds. The system also has a reactor function with a configured threshold of 60 milliseconds. Now, as long as the average latency is less than the latency threshold, everything is good, monitoring is green. And in fact, as it stands now, everything is fine. Application 1 sees an increase in latency, which in turn makes the average latency go up to 59 milliseconds. What you'll notice here is that the average latency is still less than the configured threshold, meaning that the system is showing that everything is in green, but as a matter of fact, application 1 has seen an increase in latency up 40%, right? So application 1 is in pain, although the system doesn't believe so. So there's a clear discrepancy here, and this is what gray failures is, right? different entities are seeing the same issue in a different light. So application 1, along with the other application, need to ensure they do their own detection and mitigation of the failure. So an example of grey failure is a network partial impairment. If you have a load balancer that is sending traffic across all your availability zones, and there's an issue that happens in, let's say, AZ3, an observer, because traffic is being sent across all your availability zones and touching all your resource endpoints, an observer may make the false assumption they will actually notice a 33% degradation of traffic across the board, across all availability zones. And they may they'll come to a conclusion that the entire region is faulty, but as a matter of fact, it's only coming from one AZ. Another common scenario is a poison pill. On a bad day, you might run into a situation where a client can send a poison pill that is load balanced across to all of your infrastructure and triggering an application bug within your environment. And because of this cross-AZ load balancing, coupled with multi-AZ architecture, the impact is actually cascaded across all of your infrastructure. Okay. Another very common example, and this is probably the most common one, is a bad deployment. So if you're deploying your code to your infrastructure in one go and your boundary is big, this is a big blast radius, and the impact of this could be widespread, and will it roll back, and coming back from this could be a challenge. So with these failure scenarios in place, keeping those in mind, if we have a large boundary here, and any of these scenarios happen, then the impact here is big because the blast radius is big. So what can we do here? We could further reduce the blast radius by creating smaller boundaries or cells and having a copy of our application in each of those boundaries. Now, what we have done here, if there's an issue that happens, it will only be isolated within this boundary or within this cell, reducing the blast radius and containing the failure to be only within a defined boundary. So, cell-based architecture. Each cell will have a copy of the entire application stack deployed in each cell. Cell state is not shared between each other, and data is partitioned in such a way that there's no replication between cells. And you'll have complete isolation between the cells and a way to limit and contain the failure. And plus, with cell-based, you could easily scale out your infrastructure as opposed to scaling up. So there's a few ways to design your cell architecture. The first one is multi-AZ cells, which are the cells and resources that are spanned across multiple availability zones. In this design, you'll have cross-AZ load balancing, which means that traffic is not crossing the AZ boundary. And you can take, in this design, you can take advantage of automatic recovery using native services. So we have services that are multi-AZ, which means if there's a failure, you could leverage the native AWS service to come back and recover from those failures. So now when there's an impairment that happens, the failure is actually masked, and it's hard to understand and know where this failure is coming from. We discussed this earlier when I was talking about grey failures. You have less control over an AZ failure, and mitigation becomes a challenge. Another design is the use of cells in a single AZ. And in this example, we have one cell equal one AZ. In this design, you have AZ affinity. AZ affinity meaning that traffic is pinned to remain within an availability zone and not crossing the AZ boundaries. And by doing so, you'll have more control over an AZ failure. So if there's an impairment, you'll know that this impairment is coming from one particular AZ, which makes mitigation much easier, and you'll know, you could fail away from that AZ if you choose to do so. You can actually take it further and create multiple cells within a single AZ. This obviously introduces complexity, but you further reduce the blast radius here. And by defining and managing the capacity size of each cell, you can scale out your infrastructure in a very deterministic and predictable way. And because it's managed, it's kept to a manageable size, it's easier to test your it's easier to test your components because they're confined to this boundary, and you could stress test that particular cell and not have to exceed any limits. An important aspect here is the introduction of a cell router. So you need a way to distribute your request to individual cells. And this layer needs to be performant, it needs to be resilient, and it must not be a blocker in the data path. So we talked about, just to coming back to the challenge, we want to manage, to minimize the impact of incidents. And cell architecture gives us a way to reduce the blast radius by creating smaller boundaries, right? And copying our applications within each of those boundaries that we call cells. Next up is observability. So we have a graph here that's showing the error rate for the entire site, right? So what we see in this visual is that the problem is actually not detected. It hasn't exceeded the threshold, and the problem is actually hidden here. So right now, we're not being alerted, although there's a clear problem, but we're not able to see it, and no one's being informed about it. And the problem is magnified when you have something like cell-based architecture, because then you don't even know where the issue is coming from. So in observability, we have a concept of dimensionality, right? And dimensionality adds context to your logs and to your graphs, where it can provide multiple angles for you, where you can look and understand your system behavior and your performance much better. Look in this example, we have 3 dimensions. We have site, availability zone ID, and cell ID. And the metric here can be inspected and drilled down against each one of those dimensions. So for the first graph here, this is what we saw earlier. The problem is undetected. We don't know where the problem is coming from. So we need to drill down further. So the next dimension we could drill down into is AZ ID. And now we could see that a particular AZ is at fault here. This is where the problem is coming from. Now, we can actually even go more granular. And if we have cell-based architecture, we could go by cell ID. And we can drill down, and you can see here that you'll know where the fault's coming from and which cell. And if it's a whole, if you have multiple cells within an AZ, you probably see multiple cells being impacted here. The idea here is you'll have a more granular view if you use dimensionality, and it gives you an opportunity to drill down further into your system performance. You could add more metrics, and you could build out your dashboards as a result of this. And you could actually be more granular if you want to include instance ID and include that as a dimensionality as well, as a dimension. And this is what cell observability is. Your observability stack needs to be cell aware, which will give you individual cell insights into your cells, and you could track them independently and be able to get a granular view of your system performance as a whole. Now, with all of these cells and the amount of metrics and alarms you have to set up, you may run into an alarm noise problem. And this is very common, right? Especially if you have a site-wide outage or a failure, then your operations team are going to get bombarded with lots and lots of alarms that sometimes people just ignore and say, I don't even know what to do with this, and don't even know where to begin. A way to help with alarm noise fatigue is to roll up, use CloudWatch composite alarms. Composite alarms basically allows you to roll up your alarms into one alarm, or a couple of alarms, whatever suits your use case. And now, when there's an issue that happens, especially with cell-based architecture, this is important because if you got all of these cells and all of these metrics and alarms set up, you'll see the value of setting up a composite alarm, an aggregate alarm, just to make it easier for your operations team. If you'd like to know more about this, then you could just scan the QR code here. It'll take you to, it'll go more into this topic about composite alarms. So failover. Now, with our cell-based architecture in place, and the fact we have monitoring in place and observability, and it's all cell-aware, and we know where the issue is coming from. We identified this coming from this cell or from this AZ. The next step now is to mitigate and evacuate away from this impaired AZ or this impaired cell. In 2022, we launched a feature, a service, Application Recovery Controller, Zonal Shift. So zonal shift allows you to specify an AZ ID and a resource ID, and effectively it takes the AZ out of service. Under the hood, it removes that resource, that load balancer, out of the pool, and it stops responding with an IP address, effectively taking it out of the pool, right? And zonal shift, you can turn it on and off as you see fit if to bring AZs back into the pool or remove them out. So in this case, if AZ3 has an impairment, you could easily just apply zonal shift, take it out of service, and you have the other two AZs that you could that works and can function. This is the simplest and lowest cost option that AWS offers. So going back to our challenges now, we looked at blast radius and observability. Now the next one is cell deployments. So here we introduced the concept of a single unit of deployment. And in a cell-based architecture, the entire cell serves as a deployment unit. And the idea here is once you identify and determine what your cell looks like, then you deploy a new code to that cell, and then you would, as part of your deployment strategy, you would roll that out to the rest of your infrastructure. So a single unit of deployment could be an AZ, where you deploy your code to an AZ one at a time. And in this case, if you deploy to a single AZ, you could do all your testing, you deploy your infrastructure, make sure everything's okay, that there's no failures, and then from there, you deploy out to the rest of your availability zones. Now, in a more complex cell-based architecture with multiple cells and multiple availability zones, then you have to identify what your single unit of deployment looks like, and then from there, you could deploy to the rest of your cells in a staggered way, right? So you could start off small in one deployment unit, and then increase the number as you go through your deployment lifecycle, through your pipeline. If you'd like to know more how AWS does their cell deployment, you can scan this QR code here. So just to bring it back, the main thing that we wanted to do here is minimize the impact of incidents. And we do that by introducing cell-based architecture, where we limit the impact of incidents when they happen and containing the failure to be within a specified boundary. Observability, making sure that your observability stack is stack aware. And then deployments, making sure that you kind of deploy in a staggered way to reduce the impact of a bad deployment. Cool. And with that, I'd like to introduce Paul to talk about what they did at Slack. Thank you.
Hi everyone, as Mahmood mentioned, I'm going to talk to you today about Slack's journey to cell-based architecture, focusing on our egress stack. I'm going to talk through some high-level topics, starting off with an overview of what our egress platform is and its evolution over the years. Then I'm going to talk about how we completed our migration from our existing infrastructure to our new cell-based pattern. Finally, I'll touch base on some things that didn't go quite to plan, and then cover some key learnings and takeaways that hopefully help you on your journey to cell-based architecture. So, what is the Slack egress platform? It's essentially a managed platform that provides internet connectivity to all of Slack's internal workloads. Basically, if you run a service at Slack and you want to connect to the internet for whatever reason, you do so via our egress platform. This platform is totally stateless and is made up of EC2 instances running Squid, which is an open source forwarding web proxy. Slack has taken a very different approach to our network design. We rely heavily on VPC sharing via AWS RAM, and as such, have one large VPC per region for all our workloads. Our egress stack is currently deployed to 15 regions. Across those 15 regions, we have 486 isolated egress cells. We then group those cells together to form 103 clusters across both dev and prod. Our busiest cluster in US East 1 peaks at around 70,000 requests per second, and as you can see here, our traffic pattern is extremely predictable during the week and then drastically drops over the weekend. So why did Slack want to move to cell-based architecture? What problems were we trying to solve? Overall at Slack, there's an ongoing, larger effort to move Slack's critical services to adopt an AZ affinity architectural pattern. This was being driven by a reliability goal to limit any customer impact from a failure to be less than 10 minutes. And finally, the cost of running our egress stack continued to grow at a rate much larger than our budget guidelines. Basically, we had some cost control work to go and do. So let's walk through the evolution of our egress platform. The first evolution was very simple. We started off with a single stack per VPC. We had a Route 53 DNS record, which pointed to an NLB. Behind that NLB, we had a multi-AZ autoscale group. The NLB was configured with cross-zone load balancing enabled, so if AWS suffered an AZ impairment, things would just still continue to work. However, this design had a few flaws. To begin with, as it was a single stack, the blast radius was enormous. Any kind of issue in prod had a massive impact. We were also unable to deploy any changes incrementally, nor did we have the ability to evacuate an AZ if required. For our next evolution, we simply created more clusters in every region. We allocated workloads to specific clusters, which reduced our blast radius when something went wrong. For example, it was now no longer possible for an internal system to bring down the egress stack being used by a public-facing system. By having more clusters and them having to be able to scale up and down independently of each other was a massive improvement for our horizontal scalability. And finally, this was very easy for us to add new clusters where required, which then further allowed us to reduce our blast radius. As the number of clusters increased, we decided that we would make all our clusters identical to help reduce with the operational overhead. We placed all our clusters in a given region into a single Terraform state file. This, coupled with the way our Terraform code was written, it was extremely difficult to push a change to a single targeted cluster. As this design is an exact copy of our original platform, we still had the same issues around evacuating a single AZ. So for the third and current iteration of our platform, we took a cell-based approach. Each cell would be fully self-contained. It'd have its own autoscale group, NLB, DNS records, scaling rules, and be fully self-contained within a single availability zone. The other big change we made was we split our Terraform state files to be per AZ as opposed per region. Internal teams now have two options to connect to the cluster. They can connect to the top-level cluster DNS record, which routes traffic evenly across all cells which make up a cluster. Or they can connect directly to a cell via the cell-based DNS record. Now, if the cluster DNS record is used, the platform guarantees availability. If a cell goes unhealthy, we simply route those new requests to another healthy cell in the same cluster. If a service uses the cell-based endpoint, they are guaranteed to only access that one specific cell. If that cell becomes unhealthy, then it is up to that service to handle that failure gracefully. So now let's touch base on our migration process from our multi-cluster environment to our new cell-based platform. This migration was done against a live, production, mission-critical service for Slack. And as such, reliability was a top priority in every change and decision we made. All changes had to be two-way doors with easy rollback. Most of our cutovers were handled using Route 53 weighted DNS. This allowed us to roll back our migration at any point in time, roughly within 90 seconds. During the migration windows, if we were suspected to be the cause of an ongoing issue, we would simply roll back and either fix the issue or hopefully be ruled out as the root cause. So as part of this migration, we did not want service owners to be involved and need them to make changes to migrate to our new platform. And even worse, we did not want them involved if we had to roll back. Services were already talking to an existing egress cluster via a DNS record, so we decided that this would be the perfect point to do a blue-green deploy. This allows us to shift traffic between one stack to the new stack, totally transparently and quickly to our end servers. When doing these migrations, we started off in our smaller off-peak regions, and selected our less critical clusters first. This allowed us to not only validate that our new platform was working as expected, but more importantly, it allowed us to practice our rollout and rollback procedure with minimal customer impact. So let's go through in a little bit more detail as to why we chose a cell-based pattern. As Slack continues to grow, we're placing more and more importance on the availability and reliability of our platform. In order to achieve this, we had decided that we were going to move to an AZ affinity architectural pattern and meet these three criteria. Firstly, blast radius of an issue had to be limited to within a single AZ. We need the ability to evacuate an AZ if and when required. And once a request enters an AZ, all its downstream dependencies must live within that same AZ. Now, by moving to a cell-based architecture, we want any customer impact from a failure to be remediated in under 10 minutes. So now, why 10 minutes? 10 minutes makes it impossible to have a human involved in the loop. For example, if you're now going to be collecting metrics, say every minute, you're going to want to reduce the number of false positives, so you're going to wait for 2 to 3 successive failures before paging in a human. Now, assuming a human/engineer is available, they're going to take a minute or two to find the alert, look at the dashboard, and then decide what needs to be done. Then they've made their decision, they've made a pull request, they need to get it approved, and then deployed out. By that stage, we've blown that 10-minute target, and customers are noticing our impact. Now, one major call out I want to make here is we are focusing on remediating customer impact, not fixing root cause. So just to clarify a little bit more, this means if we're having issues in one cell, instead of investigating what the problem is and fixing forward, we are simply going to remove that cell from service and work on it in the background. Now, to achieve this, we had to go and redesign and re-implement both our alerts and our dashboards to support this. So if we look back at our non-cell-based world, we had a standard set of alarms, starting off with the NLB. We had alarms that checked the number of healthy hosts registered to the target group. The autoscale group is also running health checks to validate that the services are up and running on the individual instances. From a service perspective, we had monitoring in place that spanned all nodes in the cluster, and we're looking for things like drops in requests per second, increases in 5x errors. Now, this did give us the confidence that our platform and the service was up and running as expected. But it did not give us, it wasn't granular enough to make automated decisions with. Instead, at this point in time, all of these alerts were configured to page an engineer who had to then work through the alert and fix the issue. As I mentioned earlier, we had no way to evacuate an AZ. So as long as there was an issue, customers would be noticing impact. When we moved to cell-based architecture, we realized very early on we needed multiple levels of monitoring, each showing health from a different perspective of the stack. At the cluster level, we have aggregate monitoring that spans all cells that make up that cluster. This is essentially our customer view. This is where the majority of our traffic enters our clusters, so any uptick in errors or latency is going to be noticed in this dashboard, but then also by our end customers. At the cell level, we have the exact same alerts and dashboards configured. However, they are scoped to be only for a local cell, as opposed to being spanning across all cells. Now, for us to achieve that, we had to go through and update all our logs and metrics that we admitted to add a new dimension of AZ ID, or in our case, cell ID. Once our metrics and logs had this new dimension, we needed to rethink, redesign, and rebuild our dashboards to show the differences between cluster and cell-based health. Our cluster-wide dashboard would show us what our customers are seeing. From here, amongst other things, we could see service times, requests per second, total errors, and things like that across the entire cluster. At the cell or AZ level, we would render the exact same dashboard. However, we would filter it against this specific dimension, which allows us to drill down and get metrics for an individual cell. By having these two distinct dashboards, cluster-wide and cell-based, we are now able to see what the customer is seeing, but also have the ability to quickly identify which cell is having issues and remove that from service. So let's put it all together and kind of talk through a failure scenario. Say we've made a bad config change and put to our egress stack and pushed that out to AZ1. As a result of this misconfiguration, instances begin to fail their health check from the NLB's perspective, and they start becoming unhealthy. This continues until the NLB healthy host count alarm has gone critical. This alarm is configured to do a few things. Firstly, it alerts humans via Slack and PagerDuty. This alarm is also the source of the Route 53 health check for this cell. So at this point, Route 53 will notice the cell is critical and pull that cell out of service. As the remaining cells do not have the same bad config and they have their own alarms and DNS records, any traffic sent to the cluster is now routed to the remaining healthy cells. So to summarize here, we pushed a bad change to a single cell. That cell failed its health checks and sent notifications to humans. However, at the exact time it notified a human, it also pulled that cell out of service and remediated customer impact before a human could even begin to investigate. Now, a human is still required to fix the root cause, i.e. the bad change. But that work is now no longer time critical as the failure is not customer impacting. So what happens if all cells in a cluster go unhealthy? This was a big concern for us, especially when we started relying on AWS to automatically determine which cells are healthy or not. In this case, Route 53 fails open and will send traffic to all your cells in a given cluster. This is extremely useful if you misconfigure your alarms. Spoiler alert, we did this more than once and caused notification storms, which we'll touch base on later. Finally, the last reason we wanted to move Slack to a cell-based architecture pattern was to help reduce our cost platform. By ensuring traffic stays within an AZ once it enters the cluster, we've reduced our cross-AZ data transfer cost by 90%. From a total cost perspective, we've managed to drop the total cost of the egress platform by 75% with the introduction of per cluster scaling thresholds and instance types. If you remember very early on into the multi-cluster environment world, all our clusters were identical, which meant we weren't able to tailor each cluster with the right instance type or the right scaling policies to match the traffic profile of each cluster. Now, for total transparency, not everything in this project went according to plan. We encountered two major hiccups along the way. First, if you're doing per cell monitoring without some level of alert aggregation, once multiple cells go unhealthy, you're going to get a lot of alerts. As you can see here, this is our EMR cluster, and it's having a pretty rough time. 3 out of the 5 AZs are breaching the healthy host count threshold and are now being evacuated. At this point, all our traffic from our EMR clusters are egressing out via the remaining 2 cells. Fast forward a few minutes later, and those remaining 2 AZs are in exactly the same boat. Luckily for us in this scenario, Route 53 failed open and continues to send traffic and requests to all cells in the cluster, meaning some level of traffic is being processed. Fast forward another 10 minutes, and now another 5 alerts come through. This time, it's the recovery page for each cell. So what actually happened here behind the scenes is our EMR workloads are extremely spiky and don't really do a slow warm-up time. They go from 0 to 100 pretty much instantly, and at this point in time, we hadn't worked out the correct scaling thresholds for this cluster. So the on-call engineer here received 5 alerts, 5 recoveries in the space of 15 minutes, and there was nothing they could do besides wait for auto-scaling to do its thing and handle the spike in traffic. Now, the other major hiccup we encountered along the way was with our deployment pipeline. Moving to cell-based architecture really highlighted major deficiencies in our existing process and increased the amount of time needed to deploy a change out. In our non-cell-based environment, all clusters in a given region lived in a single Terraform state file. As we operate out of 15 regions, we had roughly 30 stages to deploy a change out globally across the fleet. So as you can see here, we started off in dev, US East 1, and then promoted that change to prod in US East 1. We then, in parallel, kick off a deploy to another region, following that dev to prod pipeline. We then follow that same process to all 15 regions to ensure we have a change pushed out globally. In our new cell-based world, each AZ is its own pipeline. So we would need to deploy to US East 1, AZ1, dev, and then prod. Then we would need to do the same for the second AZ, followed by the third, and so on and so forth. Once we would finish that region, we would need to do exactly the same thing in all other regions we wanted to deploy to. This took a fairly simple deployment process and made it extremely complicated. We now have over 100 stages, require 100 button clicks, and lots of human concentration to ensure that your change has been deployed globally. So what's next for our egress platform? Well, we need to go and rebuild our deployment pipelines to remove all that extra complexity we've just added. The other thing we need to go and do is our current process for evacuating an AZ is extremely hands-on. It requires a Terraform change and needs to be deployed out via that same normal deployment process, which is not ideal. We're going to investigate leveraging Amazon Route 53 Application Recovery Controller to simplify that for us. Now, to kind of summarize this journey into a few key takeaways for you all. This evolution happened over many, many years. For us, what I've just talked through is roughly 4 years to complete. That's from when we deployed our first single stack to the final cell-based platform. Each evolution needs to solve business issues. For example, when we started off with a single cluster per VPC, we had scaling and blast radius concerns. We solved those by moving to a multi-cluster environment. That solution served us well until we had the need for targeted deploys and the ability to drain an AZ when required. Basically, we didn't decide to rebuild the platform each time just for the fun of it. It has to solve both technical and business challenges we are facing at the time. Finally, cell-based architecture may not be a perfect fit for all your workloads. For us, the egress platform made perfect sense as it was fully stateless and was very easily shaped around the AZ boundaries. And with that, I'd like to say thank you. If you'd like to know more about Slack's infrastructure, please take a look at our blog site, slack.engineering, or scan this QR code. Thank you very much, and I'll hand you back to Mahmood.
Thank you, Paul. That was very insightful, and thank you for taking us through what the Slack journey was like. Just to quickly summarize, look at cell-based architecture as a way to reduce your blast radius, right? And you could do it on a per workload perspective to start off with. As Paul said, it might not be suitable for some workloads, but try to look into how you can reduce your blast radius within your own environment. Use lots of monitoring and alerting, and make your observability and monitoring cell aware to ensure that you have more cell insights, more observability into your cells. From a code deployment perspective, look at a staggered approach to deploy from a single unit of deployment and then just grow that out. And lastly, once you identify that there's an issue, look to mitigate and evacuate the impacted cell. And with that, we'd like to thank you, and please, if you could complete the session in the mobile app, that'll be great. Thank you for your time. That's it.